Hi, and welcome to Newton's method and also the introduction to related rates, which I hear are a trickier thing. They're a very particular application of derivatives. Newton's method is a cool way that we can actually figure out x-intercepts, which was used before we had calculators to do it for us. So how did we find these goofy zeros before we had calculators? The general idea is we would use the derivative. If we found the slope at this point, we could then trace that line back to something closer to the point that we're trying to find. And then if we did that again, using this new x value, we'd be able to trace a point down again and again and again till we got closer and closer and closer to the root that we're trying to find. So in general, we have some point, x sub n and f of x sub n. And then we also can find the slope at that point. That's just the derivative of f of x sub n. And then you get this equation. And we want to try to figure out, okay, what is this new point as we move down that line? So we're going to take our equation for the line. So y equals, can I have a pen, please? So y minus f of x sub n equals f prime of x sub n, x minus x sub n. So I want to figure out, okay, well, what is this point? And particularly, what is the x value of that point? I know the y value of this point because I want to go all the way to the x-axis. So that's 0. The y value is 0. So I'm going to replace this y with a 0, effectively getting rid of it from our equation. So I need to solve this equation over here for this x. Well, the first thing I want to do is I want to get rid of this thing. So I'm going to divide both sides by f prime of x sub n. Divide both sides of f prime of x sub n. And we end up with negative f of x sub n over f prime of x sub n equaling x minus x sub n. And again, I'm trying to get this thing all by itself. So let's just get rid of that x sub n. So that x value is going to equal x sub n, because I added it over to the other side. I'm kind of writing this backwards from where I had it before. Minus that f of x sub n over f prime of x sub n. Now, this is kind of like my new point, and then I might do this again in order to get my root a little bit more accurate. So this is my next x sub n. And the way we show that is we say it's the next one. So it's one more attempt forward. And then I could repeat this process. Whatever number I got here, I can plug it into this stuff and do it again. So that is what Newton's method is. You make a guess at a point and you plug it into this formula here, your regular number over the function originally done over f prime of that function being done. Now you could work them out by hand, and we're actually going to do this a little goofy. This is like how people did this without a calculator, but I'm going to show you how to do this with a calculator. But this is actually what a calculator runs in the background in order to figure out what those roots are. It doesn't just kind of like guess its way. If it just guessed, it would kind of take forever. It needs a method of like, well, what do you mean guess? I don't know what guessing means. Do this a whole bunch of times. Oh, okay, I can calculate stuff a whole bunch of times. So here is our function. We want to estimate for all real solutions, and we want to make our answers accurate to 6 decimal places. This is what it spits out on the screen. I'm going to show you how to do this on the calculator. Sorry for the momentary switch around. I wanted to get this my calculator ready. So what I need to do is I first want to put this into my y equals area. So that is going to be x cubed. And I want to do the original function. So x cubed plus x minus 1. So you want to put your original function into x1, and then in x2 and y2, I'm going to put the derivative because I need to do the original function, evaluate it at the original function over the derivative. So that is going to be 2x squared plus 1. That's our derivative. Nope, you saw it in the last video, and I'm still doing it. I bring down a 1 less instead of the actual number. Okay, there we go. Now I've got a good derivative. Okay, then quit out of here. So we want to start at 0. So I want to put in 0 for my x value. So I'm going to press 0, and I want to store that as my x value. So x. And then I just hit enter. So it's like, okay, calculator, remember, if I type x, I mean 0. And then I want to do my Newton method. So I want to grab my x sub 1, or my original x. Well, right now I'm going to start with 0. I'm going to guess that the intercept is at 0. So I just use x. Then I do minus, and I need to evaluate this. I need to find f of 0. Well, that's just what I have in my y1 spot. So if I just do y1, then it will evaluate the function at 0. So to get a y1 on your calculator, what you do is you press vars, and then you go over here to y vars, which gives you function. And we want y1. Then we want to divide that by the derivative of f of x at the number I'm just doing, so 0. So that I put into y2. So I'm just going to do that at y2. So again, I press vars, y vars, function, and I want y2. So now I'm doing my x sub n, 0, f of x sub n, f of 0, so y1, over the derivative of f at 0. So that's what y2 is doing. It is the original function in our y area, but since I've got x here, it's actually evaluating it at that particular point. Now I wanted to remember this number that I do, so I want to store this again as x. And then I hit enter. Cool. Now x is remembered as 1. So I can do this a second time. If I hit second, enter, I can get it to do that same calculation a second time. Enter. Cool. Now I'm a little bit closer to that 0. And what's cool is you don't even have to hit second enter. You can just hit enter again, and it will repeat the previous function. So now in this one, it was grabbing this 0.05 because that's what x is now because we just stored it as that, and evaluating f of x at 0.775, the derivative at 0.75, and it created this. And it's remembering that. So I can do it again. Cool. And then I can do it again. And notice that this 6.8 seems to be the same now. So that seems to be accurate. But this 2.3, it's been accurate twice now. Let's see, 2.3, 2.3, 2.7, 2.7, 8.0, 3.9, 3.8. But as I hit this now, you can see that it's sort of stopped. It is getting more accurate, but it's not getting more accurate to the point that I can see it. I only see so many decimal values. So I actually have it accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places, but it was only asking me to be accurate to 6. So I just need the first 6 decimal places. So you can see that I already had it on my screen to begin with, but it is 0.6 682328, because I do want to round. Done. That is Newton's method.